All right, let's begin. So we are still in 3.5. And we're now to the log differentiation part. Which I described to you in steps, but I use those steps to derive a formula. Like, what is the derivative of a to the x? What is the derivative of a to the u?
A to the x.
Yeah, so this one was a to the x times ln of a, right? So again, when you see something like this, you would not try to apply the power rule because the template doesn't fit. Because in the power rule, the base is the variable and the power is the constant. Here's the opposite. The base is a constant, the power is the variable. So whenever you see something like that, this is going to be the rule to differentiate it. So this would be, and a can be any positive constant. So this would be like, if you want to differentiate 2 raised to the x, then that's going to be 2 to the x ln 2, right? As an example. Here it's a to the u. U represents any function. And so here we can apply the chain rule. So it's the derivative of the outside times the derivative of the inside. So we end up with u prime a to the u. So this would be something like, if you wanted to differentiate 2, and it's not just x, but like 2 to the x squared, then that would be 2x times 2 to the x squared times ln 2. So that's just an example. With these 2 rules, you're now able to do the 3.4 homework, but I'll make that due on Friday. Unless, did I ask for it today?
Maybe.
It might have asked for it today. I don't remember, but it's whatever. I mean, we're kind of in a part of the semester. Spring break is almost coming up. It's like, whatever. Like, it's not like I'm going to like grade it in a rush and give it back to you guys anyway. So, all right. So with these 2 rules, that allows you to do things in 3.4, which if you have the homework today, I'll take it, but if not, it's okay to give me on Friday. So these 2 rules are what 3.4 was sort of based on, but we didn't do it yet because I wanted to prove it using log differentiation, and at the point where your textbook introduced it, it didn't yet introduce log differentiation. Your textbook pretty much said, this is the rule, just believe us, but I kind of wanted to derive those for you. So we have 2 new rules to derive 2 different kinds of functions, but log differentiation is even more useful than that. It can help us in many other cases. So you've seen here, we didn't know how to deal with the situation of being a variable in the power, and so we sort of use log differentiation to get rid of that power, because logs can get rid of powers. And this is sort of a general rule. One reason in which we want to use log differentiation is when we have a power that we don't know how to deal with, but there are other situations, so we're going to kind of explore that a little bit. So these are these 2 new guys that we've done. So we're going to use log differentiation because some of these things, they don't have general formulas, even though technically we could write them down. So differentiation. Just to remind you of the steps. So this is if you're given something like y equals f of x. To find y prime, you can go through these steps, as in dy dx. 1, you can log both sides. And of course, the point of doing this is to simplify. Right? So for example, if there's a power that you don't want to deal with, you can use logs to take that power down. If there's a product you don't want to deal with, you can use logs to split that product up. If there's a division you don't want to deal with, you can use logs to turn that into a subtraction, and et cetera, et cetera. So all the things that we know about log rules in terms of simplifying them, we can apply that here. Step 2 would be to differentiate implicitly, which we spoke about what implicit differentiation is with respect to x. And then 3 is just to solve for y prime. We use this method to derive the formulas for the derivative of a to the x. Here's when you want to use log differentiation, because you don't always use it. one situation is when we have you'll notice that very few of our rules talk about having variables in a power. We now know two sets of rules when we have a constant base with a variable in a power, but in general we kind of don't. And so logs, because we know they turn powers into products, they're very useful in this sort of situation. So another question that I asked you in the quiz was, I think this was a bonus, how to differentiate x to the x, for example. Right, so this is a function where both the base and the power are variables, so they're both growing at the same time. That's a function that grows super fast. It grows faster than an exponential function. And so how do you find something like that? So once you see that, you realize that for one, the power rule doesn't work because the power is not constant. But also the previous rule that I gave you about a to the x doesn't work because the base is not constant. So neither of those general rules work. And so now I have to do something else. And what makes this complicated is actually the power, because if that power wasn't a variable, I could just use the power rule. So the power is what's kind of messing things up for me here. So I want to actually get rid of the powers. I can use logs. So here's how we do that. So if we set y is equal to x to the x, what I can then do is I can ln both sides. And that allows me to bring that power down on the right side. So to figure out something like this, I could use log differentiation. Because the power is kind of annoying to deal with. So I can get rid of those powers using logs, we know that. And so now I can differentiate implicitly with respect to x. So the derivative of ln y.
Y prime over y.
Y prime over y. Derivative of x ln x.
You said x times 1 over x. So 1 more. Which is 1. And then you move the y to the other side.
No.
Plus ln of x.
Plus ln of x. Y.
Product rule.
Product rule. So you leave one, differentiate this, that's this part, plus now you differentiate this, leave that. Right? You can't forget any of the rules. So the product rule still applies. So this now becomes 1 plus ln x. So this means that y prime over y is equal to 1 plus ln x, and now I just solve for ln for y prime. This would mean that my y prime is just y times 1 plus ln x. But my y was x to the x, so this is just x to the x times 1 plus ln x. So the slope of x to the x is this function. Did anyone get that?
Nope.
Okay, well now you know the answer.
I forgot to substitute y.
Huh?
I forgot to substitute y. back in.
You got to
But-
here?
Yeah.
Okay. Okay. So that'll be your answer. There are other situations where you want to use log differentiation. But that was one example. So here's the second case in which you want to use log differentiation. Essentially, it's going to be cases where applying all the other rules directly would kind of be too annoying. Right. So let's talk about an example of that. So for example, how would you find the derivative of, I wrote something really annoying here, radical x times x plus 1 3 over 2. And it could get even more annoying, but let's just start here. Now technically we know enough to actually differentiate that function. We could just do the quotient rule. However, you can imagine that would be very annoying because now to differentiate the top, you have to do the product rule. To differentiate the bottom, you need the chain rule. So you're going to be doing the quotient rule while doing the product rule while doing the chain rule. It's kind of going to be annoying. You're going to have fractions in the powers and also fractions all over the place. So that might not be something that you want to do because it'll just be too annoying. But the idea is logs can actually break up divisions into subtractions. They can break up products into sums. It can bring powers into multiples. So we can actually take the log of this expression and it allows us to make a lot of little simpler expressions. And each of those simpler expressions are easy to differentiate and we can apply the sum rule to those expressions. So here, if my y is equal to radical x times x plus 1 to 3 over 2 over 2x squared plus 7 raised to the 7th, what I could then do is log both sides. So instead of actually going through the quotient rule, and this kind of reminds me of a lesson I put on the previous test that you guys took, where I asked you ln of something and then I asked you to differentiate ln of something. The idea was using the ln, you could break it into smaller pieces and then you just differentiate each of these pieces. So it means the right side could become, how would the right side look?
ln of the top minus ln of the bottom.
So let's just go through the steps here. So it's ln of this. And I mean, the more used to this you are, the quicker you'll be able to simplify. You can probably even start skipping steps, but let's actually just write this down. So you'd be able to do that, right, where all of this is inside the ln. And then what would you be able to do?
Differentiate this.
Oh, I'd break that down even further before I start derivatives.
ln of radical x plus ln of...
Yeah, here we have a product, so I can take this as ln of radical x plus ln of x plus 1 to the 3 over 2 minus ln of 2x squared plus 7. Now what?
So you prime over u for all of them?
Yeah, but it's still, I still think it's going to be a little too annoying. We can actually make it even simpler. Yeah?
You can take the powers out, so 3 over
You can take all the powers down. And so you don't have to do the chain rule when you're doing the derivative thing over the thing itself. And so here this is x to the half. I can bring that half power down, so this is just 1/2 ln x. Plus I can bring this 3 over 2 power down, that's just 3 over 2 ln of x plus 1. Minus I can bring that 7 power down, that's just ln of 2x squared plus 7. Right? So this guy is actually the same as this guy, where this guy would be super annoying to differentiate directly using our rule. Taking u prime over u for this guy would be super annoying. But doing u prime over u for each of these individuals is not super annoying. In fact, it's pretty easy here. So what we would get then is, at this point I'm going to differentiate both sides. So remember there's an ln y over here. I will differentiate both sides implicitly with respect to y. The derivative of ln y would be y prime over y. What's the derivative of half ln x? 1/2 times 1 over x, right? Differentiating ln, so that's 1 over 2x. Derivative of ln of x plus 1?
1 over x plus 1.
Is 1 over x plus 1. So that just becomes 3 over 2 times 1 over x plus 1. And the derivative of ln of 2x squared plus 7?
4x over 2x.
4x over 2x squared plus 7. And then there's a 7 in front. So it's just 7 times this.
Wait, why is the x plus 1 in the denominator?
Huh? I have 3 over 2 times 1 over x plus 1. I just multiply the fractions for this part here. Just write this to be a little less annoying. I can take that 7 times the 4. And that's what, 28? And so now I can say that my y prime is going to be y times this guy. Or this is radical of x times x plus 1 to the 0, 2 over 2x squared plus 7 to the 7th times and anyone interested can actually try to do that using the quotient rule and compare our answers. Right? And by the way, when you actually get used to actually doing this, like especially if you do a lot of homework problems and you practice a lot more problems, like to jump from this step to this step, you can actually do pretty quickly. A lot of students will even be able to, with enough practice, do that in one shot and just go straight from here to here. And then the rest of it is just sort of easy. So that's how we want to use log differentiation. So there are cases where we have a power that we don't know how to deal with, we use log differentiation. Or we have a situation where doing the product or the quotient rule will be super annoying, and so I use logs to break up the divisions and the multiplications. Before moving on, I want to talk about one alternative to log differentiation. Any questions on this before we move on?
What's the last thing you wrote? Is that just a,
Oh, I just replaced y with the original function. So here you can tell about an alternative. So it's really sort of a personal preference kind of thing. Some people might like this other than logging both sides and then doing this and then multiplying by y at the end. Some people might like doing this way. And there are situations where it's nicer to do this, but I'm not really going to test you on problems like that. Even though I had a couple of examples here, I probably won't test this class and something like that. Use the fact that e to ln of anything is just
X.
It's just a thing. Exactly. Right. E to ln of x is just x, or e to ln of literally whatever expression you put there that can work in the logarithm is just the expression that you put in the logarithm, because e's and ln's sort of cancel each other. And so if I wanted to find the derivative of x to the x, I can realize that this is exactly the same as finding the derivative of e to the ln of x to the x, because x to the x is the same as e to the ln of x to the x. I can actually just write that expression in, right? This thing is the same as e to the ln of that thing. In which case, I can use my log that's in the power to start simplifying things in the power. And now I'm kind of just focusing on the power. And so I have that guy to differentiate. How do I differentiate this guy, e to that?
you prime e to the u.
Exactly. At this point, I'm going to apply the rule. The derivative of e to anything is just the derivative of the power times the original function. So that's what I'm going to do. I'm going to take the derivative of the power and multiply that by the original function. Now, derivative of the power is me doing the product rule. So differentiate the x, leave the ln, plus leave the x, differentiate the ln, you would get 1. And the original function is really just me rewriting x to the x, and you get the same answer. So there's another trick where you can write any expression, as long as it's positive, as e to the ln of that expression, and then you can use this rule to find the derivative. So that's also an option. So that's a sneaky way to get an ln inside of something to simplify. Okay, so it's sort of an alternative. You do this in any situation where you do log differentiation, you can also do this. Yeah, that's kind of all I want to talk about log differentiation. Any questions on this? Yeah, so you just go through the homework, do a few problems both ways, and whichever way you prefer, just stick with that way and forget the other way. Right, so you can either do log differentiation or you can do something like that. And that ends 3.5, so the homework for that is due on Friday. Yeah?
Can we go over a problem that was in the quiz that had ln in it?
Sure.
Sorry. I think that was in the second part, the second problem.
Oh yeah, so the next topic we're going to cover is actually the last topic that's needed for the next test. Okay, so I just want to make sure of that. So it was which in problem 2? Oh, the implicit differentiation one?
No, I think the one on top of that. Yeah.
Oh, the derivative of x times e to the x times ln x, that one?
I think so, yeah.
Okay. Anyone think they did it the right way?
Can't you just
Yeah?
attach the x to the x as like a coefficient and then do the product rule?
Yeah, you can do the product rule here. So how did you apply that?
So x e to the x times the derivative of ln x.
Okay, so you thought of this as one function and that as the other function?
Mm-hmm.
Yeah, you can do that. Just do the product rule and split them up. So it means you would leave the x e to the x times the derivative. So this is your f and this is your g. So this is your f times, now we're going to do g prime.
It's just 1 over x.
It's just 1 over x. Plus,
Plus ln x.
now you're going to put your f prime times the g, which I know here is just ln x. But what is f prime?
What did I do?
X e to the.
Yeah, I think I just left it.
Do you have the product rule again?
You need the product rule to find the derivative of f. Because then f is a product of two functions. So you need the product. So you differentiate the x, leave this, plus you leave the x, differentiate that. So that would be the answer. Or it's something like x e to the x times 1 over x plus e to the x ln x plus x e to the x ln x.
If no one got it right.
Or you can, then no one got it right. What do you want to do?
Yeah.
Could you also do it where you just make x f?
X e to the x ln x.
So I have a question.
So yeah, you can break it up in any form. You can let these two consider it as one function, that as the other function.
Yeah.
Those two consider it as one function, that as the other function. But the idea is just split it into two groups and do the product.
What I did.
Yeah.
was I did the product rule for x to the e to the x, and then I changed ln x to 1 over x. Would that be incorrect?
So you just did the product rule here and then put 1 over x there?
Yeah.
So no, that wouldn't.
No.
You need to do the product rule before to that. Here's something that's neat. The product rule actually generalizes to any finite number of functions. So there was a time where I sort of mentioned, now you could have done this, that wouldn't be the thing, but you can actually think of like a generalized product rule. There was one time where I mentioned, oh, the product rule is just like the sum of the things where you take derivative of one function at a time. You can actually apply that rule in general. So essentially, that will always be your answer. And this will work for no matter what the length of the product. So I can say, I want to differentiate the product of 3 functions. And I can just, I keep adding this expression over and over, but I take a derivative of a different person each time. So this would be f prime times gh plus f times g prime times h plus f times gh prime. And I could do the product rule on 4 things if I want to. So f, g, h, I. And I can, this is f prime times gh I plus f g prime times h I plus f g h prime I plus f g h I prime. You can just keep going, right? You add up a bunch, you add up the term, but you take derivative of one function at a time. And so in that sense, the quickest way to do this guy would be to apply that rule. Differentiate the x, leave the other 2. Plus, differentiate the e to the x, leave the other 2. Plus, differentiate the ln x, leave the other 2. And that would also be the answer. But barring that, you can just split a product up into 2 pieces and apply the product rule. And if you apply the product rule over and over, you'll eventually get to the answer. So in the next 15 minutes, we're going to start the new topic. A little bit of conceptual thing to talk about in the beginning, but let's see how far we get. So this is 3 point, we're actually going back to 3.2. Linear approximation and marginal analysis. So marginal analysis is usually applied in like a business/economics context, but you can apply it to other contexts as well. So we'll talk about that. We'll also talk about linear approximation. This is really talking about what tangent lines are good for, to use them to approximate functions. So we're going to sort of look at that from a systematic point of view. So let's start with linear approximation. The idea is to use a tangent line to approximate the change in a function. Of course you want to do this when dealing with the function itself is kind of annoying, but here's kind of the picture of why something like this would be useful. So let's say this is my function. It's doing this thing over here, that's your f of x. Here's one point in time that I currently know what's going on. Let's call that where x equals a. And there's a point in the future, let's call that an x value. where I don't really know much about that point, but I want to kind of figure out some information about that point, right? Now, the difference in, here's some notational thing. I was going to use it. If you look at the difference between these two y values, that difference, the notation they use for that is delta y, right? Which is sort of change in y. That's the uppercase Greek letter delta, right? So that's called the change in y. Right, like the actual change. So you can actually take the difference in these y values, that tells you how much your function changed. But sometimes dealing with the y values by themselves is kind of annoying because the y might be very complicated. So what you can do is, at this point where you have a lot of information, you can create a tangent line. And so you can figure out a point on the tangent line for the x value that you care about. Now, the difference between the old y value and the tangent line, that difference has the notation dy, meaning derivative, right? That's the distance given by the derivative of the function. Right? And the idea is, if we don't go too far away from the original point, the difference between delta y and dy will actually be very small. I can actually use this difference to approximate that difference. You'll notice that if I zoom in, for example, here and here, those two are not that far apart. And the closer I get to this point, the more that becomes true. Right? So, idea is to use our dy to approximate the delta y, right? So there's an actual change that can be measured, and there's an approximation of that change that can be measured. So the actual change will have to be dealing with the function itself. The approximation to the change, we're dealing with the derivative or the tangent line, right? And the usefulness of that is a tangent line is just a straight line. It's y equals mx plus b. That's one of the easiest functions we know how to deal with. We know everything about that function. Okay? And so a lot of times using the tangent line is it's a lot easier than actually using the actual function because the definition of this function might be very complicated and very annoying to work with. And of course, in context where you'd apply this would be, I mean, we're going to do things by hand, but usually in context where this sort of idea would be applied, it will be applied in situations where you couldn't even talk about it by hand because it's so complicated. So you kind of program this idea into a computer, and the computer will kind of use derivatives to figure out what's going on with the function itself. Which I'll probably mention a little bit more about that next time. Talk about some applications of this. Right, but in this section we're really going to be talking about a lot of ideas which will kind of hint to you why, for example, business majors or finance majors need calculus. It'll be a combination of statistics and calculus and what that can mean with crazy functions. Because if you look at like a stock chart, that's a very complicated function. You can't even find really a formula for that function. Everything seems random, but it's not. Right? You can actually use calculus to kind of approximate things and figure things out in the future. Right? So it's not a coincidence, in other words, that all these big banks make money, right? It's because calculus works, and they know what's going on here, so they can kind of predict what's going on in the future using calculus, and so they know what stocks to buy or what stocks to sell. And anyway, let's move on. But that's the idea. We're going to use the difference between the tangent line to talk about the difference in the actual value of the function, and this approximation can get pretty good if we're very close. So here's a formula we can use. It's the linear approximation formula. This is the formula that I asked you about at I think it was also a bonus problem on the quiz. Yes, I asked you, this is a bonus problem on the quiz. Okay, so here's how we're going to do it. Let's talk about the derivative at this point. Right? So if you were to take f prime of a one way you can do that by the definition is to do the y2 minus the y1 over the x2 minus the x1, and you actually take the limit as the denominator goes to 0, right? That's one definition of the derivative. Now this is as you're taking the limit. Now if x is close to a, then limits talk about getting close. So what ends up happening is, basically what the limit is going to tell us is that the derivative at that point is going to be approximately equal to this guy. The closer the x and the a values get to each other, that's their closing distance, then the derivative will be approximately equal to this guy, right? And we're talking about getting super close now. And so basically what we can do is we can just use that formula. So we start out with the derivative formula, using the other version of the difference quotient. And so basically what this means, I can solve for f of x. Right? Just move this to that side. So you'll end up with f of x is approximately equal to f of a plus f prime of a times x minus a. This is called the linear approximation formula. That was the answer to the bonus formula. This is the linear approximation formula for f of x at x equals a. One thing you can notice is that if I take the function y equals f of a plus f prime of a times x minus a, that's actually the equation of the tangent line. Right? Take y minus y1 equals mx minus x1. The m is given by the derivative, and that would be the equation of the tangent line. So we're essentially saying this idea leads to the fact that our function is almost the same. It gives us almost the same output values as the tangent line does. And so we can actually use the tangent line as an approximation for the function. So if I know what's going on at the point A, I know its value, I know its slope, I can figure out what's going on at some point in the future, some point away from A, provided it's close. Right? Because the limit gets better when you're inching close to something. Right? So the closer you are, the better this approximation gets. That's also something I need to. I should probably write that down. So in the future, and of course I will be testing you about this on a quiz, if I ask you to state the linear approximation formula, this is the formula I want you to state. Right? It's the formula that says f of x is approximately equal to this expression when my x is close to a. And it's called the linear approximation formula for f of x at x equals a. Let's actually use it. We only have time for like one example, but we'll do more. And for this topic, this is a typical kind of question you will be asked to do. So you can see an example of a kind of question that I can ask on a quiz or a test here. Use linear approximation to estimate the square root of 3.99. Yes, A is 3.99. So that would be an example of a question. Now when you're faced with such a question, you realize that you need to use linear approximation, or I'm asking you to estimate something. You're going to use the linear approximation formula. So now you need to actually develop that formula. So one thing you're going to talk about is what function would you want to use? Okay, so if I wanted to approximate the radical of 3.99, what's a nice function you think you'd use here? What would you guess is the function? Square root of x. Okay. So here what you would do is you'd set f of x equals the square root of x, right? What you want to approximate, we want to approximate f of 3.99, right? That's going to be our goal. So I choose a function to look like the kind of expression I want to approximate, which is going to be this function. And really what I want is, what is the value of this function when I plug in x equals 3.99? Now I don't know that off the top of my head, and I don't really know what the answer is. But now, the next thing you want to do is choose A, which is close to our x value. Now you don't know the square root of 3.99, but is there a number that's close to 3.99 that you know the square root of? 4, right? The problem wouldn't be a problem if that number was 4. So now, in other words, what I'm saying is my x is 3.99, but I don't really know much about that point. Let's actually use the point 4. So I'm going to take A to be the point 4. That's a nice point that I know about all the information. I can figure out what is the value of the function at 4. I can also figure out what the derivative at 4 is. So here's what I'm going to do. I know that the radical of 3.99, that's going to be my f of 3.99. And again, I don't know what that is, so I'm going to approximate it. Now f of 3.99 is going to be approximately equal to, here's where I'm going to apply the linear approximation formula. Right, what is that formula? That's the formula that says f of x is approximately equal to f of a plus f prime of a times x minus a. So I'm literally going to be plugging those in. Here my x is 3.99, so I'm going to plug in my a. So that means f of 4 plus f prime of 4 times 3.99 minus 4 is going to be my approximation here. So now what is f of 4?
2.
This is just radical of 4, which is 2. What is f prime of 4?
1/2 4 to the negative 0. Oh, it is 0.
No. We know that, what is f prime of x? Let's start there. It's 1 over 2 radical x, which means that f prime of 4 is 1 over 2 radical 4. Now what is that? That's just 1 over 4. That's just a quarter. And so now I can actually go and plug this in. So this means that the radical of 3.99 is approximately equal to 2 plus 1 over 4 times 3.99 minus 4 is roughly minus 1 over 100, right?
Yes.
Right, because that would be like minus 0.00, and you would get that. So this is going to be 2 minus 1 over 400. Or in other words, an approximation for the radical of 3.99 is going to be 799 divided by 400. What is that actually? By the way, this guy is 1.9975. You know what the actual answer is?
1.9976.
1.997. No, it's actually 0.75.
Wow.
7498. Now I did that without a calculator, and I was right up to like 4 decimal places rounded. Right? So that kind of tells you how good a tangent line approximation can be. We'll pick up with more examples next time.
Can we hand it over?
The homework for 3.4 you can give me now or Friday. Okay.